Hello, welcome to the playlist of videos on essential statistics for data science. I am Hemakumar Kasala, and in this video, I wish to explain you all about sampling. The primary challenge that an effective sampling should overcome is the bias. There are three forms of bias that one needs to understand: selection bias, measurement or response bias, and non-response bias. We'll understand each one of them in detail. The next thing that one needs to understand is about various methods that are known to implement sampling: simple random sampling, stratified random sampling, cluster sampling, and systematic sampling. We'll understand each one of them in detail, their pros and cons, and when to choose which method. Let's get into the video. Statistical studies, as discussed in the previous videos, are carried out on sample data that is sensibly extracted out of the population data under the study. The conclusions that are arrived based on the sample data are finally generalized to the population. Hence, it is all the more important that the sample represents the population to a truest extent. Samples are never judged by their composition, but by the process by which they are derived. To begin with, the process involves understanding the possible deviations that can occur in a sample as against the population as a result of one, incorrectly composed sample and or incorrectly interpreted data from a sample. And secondly, the process involves choosing the correct sampling methods to arrive at more representative samples. Deviations as a result of incorrectly composed sample and incorrectly interpreted data within a sample is called the bias. Primarily, there are three contributors to the bias. 1. Selection bias. 2. Measurement or response bias. And 3. Non-response bias. Let's understand each one of them in detail. Selection bias. As discussed, sample should be a true representation of the population. In other words, this unselected part of the population should not systematically differ from the sample, that is, the selected part. For example, when the sample fails to include people who are homeless, or those who do not possess a car, or those who do not have a telephone connection, etc., when the study involves a population in a given locality. Additionally and importantly, if the selected attributes of the population under the study differ significantly between the sample and the rest of the population, then a selection bias is said to have occurred. Sample as a result of voluntary choices or mechanisms can potentially result in selection bias. Voluntary candidates in a sample seldom covers the diverse spectrum of characteristics from a population. Measurement or response bias. Measurement or response bias may occur in the process of extracting information from the selected sample, that is, post-selecting the sample. Measurement bias happens in circumstances where measurements are made using instruments or devices that are improperly calibrated. On the other hand, response bias happens generally in cases where responses are sought from individuals in the sample. Bias occurs in these cases because of the ways the questions are designed for which responses are sought. Influences of the people or organizations posing the questions, and lack of truthfulness in the responses. Non-response bias occurs in cases where responses are not obtained from all individuals in a sample. Some or more responses are left out. Non-response bias occurs when the responses from those received differ significantly from those who are left out. Non-response bias is similar to selection bias in the way that some significant responses are missed out. So any of the above forms of the bias is caused by 1. The way in which the sample is collected and or the way in which the information is gathered from the sample. Rest of the video focuses on sampling methods that help solve the selection bias issue mentioned in point number 1 above. Convenience should never be the approach in sampling. For example, one may find it convenient to consider the set of students attending the statistics class as a sample to undertake some study in a university. But such a sample will more often fail to represent the whole university, since statistics as a subject may not be opted by students from all disciplines in the university and also may not include all levels of seniority in the university. Convenient approach in sampling thus results in choosing wrong samples. Hence, we need formal sampling methods. Simple random sampling is the most often used sampling method. Simple random sampling by definition means any sample of size n stands an equal chance of being selected amongst all possible samples with unique composition of size n. Individual elements are randomly chosen each time a sample is created to make the above requirement possible. Also means every element in the population stands the same chance of inclusion in a sample. Aim of the simple random sampling is to obtain a sample that is true representation of the population. But simple random sampling does not always guarantee a true representation. Simple random sampling at times or on fewer occasions can result in incorrect samples. For example, consider the case of a classroom containing 40 male and 60 female students. A simple random sampling with sample of size 10 may result in all 10 females and 0 males, all 10 males and 0 females, 9 males and 1 female, and a few more of such skewed samples. Thus, simple random sampling at times may result in a more homogeneous sample out of a fairly heterogeneous population, and vice versa. Hence, there are indeed possible risks associated with such non-representative samples derived out of simple random sampling. Such risks are, however, assessed using probability methods that we will discuss in the later videos. Hence, despite risks on rare occasions, with probabilistic risk assessment, one should be able to generalize the conclusions from the sample to the population with certain level of confidence. Simple random sampling is carried out in one of the two possible ways: sampling with replacement and sampling without replacement. Object or individual chosen for a sample is replaced back in the population in case of with replacement, and object or individual chosen for a sample is not replaced back in the population in case of without replacement. Sample may contain duplicate objects in case of with replacement. Sample contains unique objects from the population in case of without replacement. Without replacement is the more commonly practiced method. However, assuming a big enough population, there's no difference between the methods as long as the sample size is not exceeding roughly 10% of the population. Can a small size random sample truly represent the population? Considering the size of the simple random sample, which can be as low as 1% or so, It is natural that one wonders if the sample can truly represent the population. Evidences show it can. Here is an example of the dot plot of the math scores of 5,000 candidates, which is the population in this case, applying for a state university. Here are the dot plots of samples of various sizes n drawn using simple random sampling from the above population. One can see the mean and the spread of the samples of varying sizes ranging between 50 to 1,000 fairly coinciding with the mean and spread of the population. Hence, as long as the sample size is not too small and the population size is big enough, simple random sampling provides a fairly true representation of the population even with smaller sample sizes. Note, the illustration here excludes the possible non-representative samples cases discussed a while ago. Though simple random sampling as a method is widely suitable and convincing to eliminate the selection bias, in different settings, the other alternative sampling methods might qualify as a better choice, namely stratified random sampling, cluster sampling, and systematic sampling. Stratified random sampling. If the population under the study consists of non-overlapping and in certain ways distinct subgroups, then it might be useful to split the population into those respective subgroups and implement simple random sampling on each of the subgroups and undertake the statistical study. Conclusions are arrived on the characteristics of each of the subgroups using the individual subgroup samples, and the conclusions on population on the whole is arrived by merging all the samples of the individual subgroups. Each subgroup is called as stratum and subgroups together is called as strata. Carrying out simple random sampling on each of the strata as just explained is called as stratified random sampling. Exploration and conclusions on the characteristics at relatively homogeneous subgroups level is more informative and revealing than the information processed from a heterogeneous population in selective cases. Don't forget, we don't miss out on the information at overall population level, just that we process a lot more useful information at every subgroup level. Stratified random sampling example. Arriving at the mean income level estimate in a given population with diverse income groups, though useful, could be less insightful at times. Stratified random sampling, on the other hand, can provide more insightful mean income level estimate per stratum. Cluster sampling. When a population is organized in terms of cluster, it is possible that sampling is done by choosing a set of clusters in random. Sampling thus done is called as cluster sampling. The number of clusters chosen for a sample depend on the size of the clusters and heterogeneity within each cluster. More heterogeneous the clusters are, less shall be the number of clusters required within a sample. The similarity between cluster sampling and stratified sampling is that both work on the concept of subgroups within a population, where subgroup equals clusters in case of cluster sampling and subgroup equals strata in case of stratified sampling. The primary and important difference is the subgroups are heterogeneous in case of cluster sampling and homogeneous in case of stratified sampling. Systematic sampling. When a population can be organized in a sequential arrangement like a list, then it is possible to implement a systematic sampling. In a systematic sampling, a random object is chosen among the first k objects or individuals from the sequenced population, and every kth object or individual is chosen from the first chosen object or individual until the end of the list into the sample. The value k will decide the size of the sample for a given population. Sample size equals population size divided by k. Value k is altered to arrive at the right sized sample. The systematic sampling works reasonably well in a population where there are no repeated sequences of records or data. In case there are repeated sequences, the systematic sampling may result in a non-representative sample. That brings us to the end of the session on sampling. Please leave your comments if any, and I'll revert back with my response as soon as possible. See you with the next video soon. Bye till then.